Alright, so let's go over the problems that you practiced to make sure that you understand the concept of mole-to-mole stoichiometry and the mole ratio. So for our first practice problem, it said lithium hydroxide, or LiOH, is a compound used in space vehicles to remove carbon dioxide gas from the atmosphere by the following chemical reaction. So LiOH, or lithium hydroxide, plus carbon dioxide gas will produce something called lithium carbonate plus liquid water. So if we have 584 moles of carbon dioxide that's present in the spacecraft, how many moles of LiOH are needed to get rid of all the carbon dioxide present? It even gives us a little warning there to remember to balance the reaction. So let's go ahead and make sure that that thing is balanced first. We have two lithiums on the product side, so we need two lithiums over here. Again, I advise using the chart method for you guys since you're probably not comfortable enough to balance these by sight just yet. But that goes ahead and that will balance everything out for me. Just by adding the 2 in front of that LiOH. That gives me my two hydrogens on the right. That takes care of my giving me 4 oxygens on both sides and balancing out everything else. So anyway, it's balanced now. Now we can move on to our stoichiometry. So we need to know how much how much lithium hydroxide we need to get rid of all that carbon dioxide in the air. We know that we have 584 moles of CO2 that's present, and we can use that relationship called a mole ratio as our conversion factor between the lithium hydroxide and the carbon dioxide in our reaction, which is just a little recipe for us, right? Whenever we do dimensional analysis, we know that whatever unit we start with has to go on the bottom to cancel out. So we know that the moles of CO2 is the first part of our mole ratio. And we want to use the mole ratio that's going to compare moles of CO2 and moles of lithium hydroxide. So we know that for every 1 mole of carbon dioxide, I will always need 2 moles of lithium hydroxide. So for every 1 mole of carbon dioxide, I will need 2 moles of lithium hydroxide. That will cancel out my moles of carbon dioxide, and that will leave me with how many moles of lithium hydroxide I will need. So my math is pretty straightforward. I'm multiplying 584 by 2. And I will end up with 3 sig figs, since that is what I have here. My answer is 1170 moles of lithium hydroxide. Alright, next problem. I think I skipped one here. There we go. Next problem is milk of magnesia, which is magnesium hydroxide, is often used as an antacid medication, as it neutralizes hydrochloric acid in the stomach based on the reaction below. So we have magnesium hydroxide reacting with HCl, which is hydrochloric acid, and this makes magnesium chloride in water. So if the stomach contains 12.6 moles of hydrochloric acid, how many moles of water will be produced as a result of taking this medication? And this is assuming that we take enough medication to neutralize all the acid, and that's important. What should we always do? We should always make sure that this is balanced. Well, I've got 2 chlorines over here, which means I need to have 2 chlorines over here. So let's make sure that we do that. So it gives me 2 hydrogens on the left, plus another 2 from the hydroxide. So I need 4 on the right. So that gives me 2 oxygens, which balances my oxygens out. So now it looks like everything's balanced. Okay. So I know that 12.6 moles of HCl are present in the stomach, And I know that the magnesium hydroxide is what is neutralizing it, but what I really want to know is the amount of water that's being produced. So I know that I'm taking enough magnesium hydroxide to get rid of all those 12.6 moles. So I'm going to use the relationship between magnesium, or the relationship between hydrochloric acid and water, to determine how many moles of water is going to be produced. So always use what is given to me for my unit on the bottom, so it cancels out. And I know that for every 2 moles of hydrochloric acid, I'm going to produce 2 moles of water. So my mole ratio is 2 to 2. Now, you should well know that 2 divided by 2 is the same as 1 over 1. So you could just as well put 1 divided by 1, but you're going to get the same answer either way, right? So our moles of HCl cancel out. And 2 divided by 2 is 1. So we can just as well write 1, and that means we're just multiplying by 1, which gives us 12.6 moles of water. So that's how much water we're going to produce as a result of taking this medication. All right, one final problem you had to practice. Ammonia. So ammonia is a cleaner that you might be familiar with, and its chemical formula is NH3. It's commonly used as a cleaning agent, as I just said. It's produced by the following reaction. Nitrogen gas plus hydrogen gas makes this ammonia. Now, the problem states that if we have 6.03 times 10 to the 4 moles of this ammonia, that's how much we want to make. How many moles of hydrogen gas do we need as a reactant to produce that amount? What do we always want to do? We always want to check if it's balanced. Let's see, we got 2 nitrogens on the left. Oh, we need 2 on the right. So let's go ahead and add 2 here. And that gives us 6 hydrogens, so we need to put a 3 there to balance it. So now we have a balanced chemical reaction. We can get to work. So we know that we want to have 6.03 times 10 to the 4 moles of NH3 made. And our goal here is to figure out how much hydrogen we want to be able to make that amount. So we're going to use the mole ratio relationship between hydrogen and ammonia. Moles of NH3 must go on the bottom because that's what we need to cancel out. And the mole ratio we're going to use, again, is between ammonia and hydrogen. We know that for every 2 ammonias, there's 3 hydrogens. So every 2 moles of ammonia, there's 3 moles of hydrogen gas. And that's going to give us what we want. So here we have to actually first multiply 6.03 by 3, and then divide it by 2, and that's going to give us our answer times 10 to the 4th. And we, of course, need to make sure we do this to the right number of significant digits. So we have 3 sig figs here, right? So we need to round this number. So we have we got a 5 with nothing after it. We have to remember our 5 rule. So if it's a 5 with nothing after it, that means we need to keep it even, right? So it's already even, so it's going to stay 9.04 times 10 to the 4 moles of hydrogen gas. There you go. Mole-to-mole stoichiometry. We'll get plenty more practice.